astronomers, which I'm a former member of. This is a wonderful presentation, very much along the lines of OCA interests. Nevertheless, a wonderful presentation this evening. Let's see. We'll start in a few minutes. I was going to present Dr. Black, who's going to present our speaker. Here he comes. There are volunteer opportunities I want to mention. There are possibly job possibilities as well. If anyone is looking, let me know after the presentation. I'd like to be able to look you up. Take a look at our website as well. There are links there. We have more people coming in. That's good.
Now, speaking of jobs, we've started a email list.
This is Dr. Black, a long-time volunteer of this chapter, past chairman. He's done everything at one time or another. Probably still does.
It wasn't me, this is somebody else. We've created a mail list for senior engineers and middle-level engineers on the IEEE website. If you're looking for work, or you're upwardly mobile, and you're in the senior category, please put your name on the list. You just go to the occs.ieee.org website and go down to the very bottom. I think it's item 3 or 4 on the list of email lists there, and click on it, and you'll get your name added to the list. Western Digital just announced they're looking for 20 senior level engineers, software engineers, firmware engineers in the 6-figure range. They told me in confidence that the jobs that can start at like 135 and go up to 185, but I would not repeat that. Panasonic has some 6-figure jobs available also. Their IFE department in flight entertainment, they don't pay quite as well as Western Digital. And again, you didn't hear that from me. And we're going to do and I would like your help too. If your company is looking for engineers, it would really help all of us. Oh, Pierre, how you doing? Your company is Telos. And you're looking for engineers too?
Yes.
Can you have your hiring manager write something up for our email list? It's the same thing we did in 2005.
You did have some cards.
And she would like to talk to whoever that you already put on the jobs.
Okay. You're doing this now, right?
Yep.
You're gutsy. You'd call somebody, right? Yeah. So the other thing I need help with is that a lot of our engineers are just too shy to cold call, and and get rejected. So we're looking for volunteers. I've been doing this. I'm talking to Michael about doing also. It's calling human resources departments of the companies and making arrangements for the hiring managers to post these jobs to our list. The virtue of doing this for the HR department is you guys have been pre-screened. You're all electrical engineers. You're already senior level, guaranteed. You've got your at least a bachelor's degree. You've got 10, 15 years of experience. You would die to get your names and your resumes. I mean, you have no idea how much they pay to try to find you guys. Makes their job so much easier. So, so it's easy to call up HR people and talk to them because they really want to find out. So if we can get those people to start posting jobs, get a nice flux, a nice flow through our mail list, that would be to everybody's advantage. And if you go to occs.ieee.org, Orange County Computer Society, OCCS, and we all do, of course, we have IEEE printed on our brains.org, then there'll be some information there if you want to click on one of those lists. Okay, it looks like you've finished dinner. I would like to take this time to introduce Dr. Lance Benner. Dr. Benner has got his AD degree in physics from Cornell in '87 and his PhD in Earth and Planetary Science at Washington University in St. Louis in 1994, which I hear is a very good university. and he's been at JPL since 1995. Now, I have heard through the grapevine that James Bond's Golden Eye was filmed at the Goldstone system radar, which is about when you got there.
Arecibo. It was at Arecibo and Puerto Rico.
Really? Well, you just ruined my whole... See if I invite you back. How about Carl Sagan's Contact?
Arecibo.
Yeah,
Arecibo.
And also the very large array.
Oh, well, so much for that pattern. Okay. Dr. Benner is a research scientist at JPL Pasadena NASA facility. He specializes in radar imaging of near-Earth asteroids using both Arecibo and NASA's Goldstone radar facility, which is up in Barstow. He has authored more than 50 papers, has participated in observations of more than 200 near-Earth asteroids. He served on the National Research Council that authored the report Defending Planet Earth. There's a copy of it right here. And he'll tell you about these pieces of asteroids and meteors and these figures that are up at the front if you want to take... I don't know how we're going to do that without totally... maybe wait till after the show. Okay, so we'll give a warm welcome to Dr. Benner.
Can we dim the lights a little bit? It'll help us see the images within the show. Especially when it's lights.
Right there.
Yeah, that would be a good one to do.
Do we know how?
That's the,
Okay, well, I'll go ahead and start over. So thank you very much for the invitation. I want to give you a quick overview of where we're going to go tonight. I'm aiming to speak for 45 minutes to an hour. I'm going to start with a brief introduction. I want to then tell you some things about near-Earth asteroids, some things that we know about, thank you very much, about their physical properties, the different types of them, what they're made of, how they rotate, how many there are, about the impact risk. I'm going to say quite a bit about that. And then in the second half of the talk, I'm going to plunge into radar observations, which is my own field of expertise. And before I continue and forget to say it, after the talk, please feel free to come up here to the front. We have some show and tell. I have a number of scale models of real asteroids up here, objects that we have observed with radar, and use radar images to estimate their three-dimensional shapes. We have some of our original research papers, and I have some meteorites. These are pieces of real asteroids, more than 4.5 billion years old, billion with a B. You're welcome to come on up and have a look at those. They have a little thing that describes each one of them. So please don't forget to do that after I finish. Okay, so a little bit about terminology. We have arbitrarily decided to define a near-Earth asteroid as one that approaches within 0.3 astronomical units of the Earth. Or more appropriately, that its closest approach to the Sun, its so-called perihelion, is less than 1.3 AU. 1.3, an AU is an astronomical unit, which is Earth-Sun distance, which is 93 million miles or 150 million kilometers. Within the near-Earth asteroids, there were three groups that we recognize, again, somewhat arbitrarily. They're named after the first asteroid that was discovered in each group, the Apollo type. They have a semi-major axis, that's their average distance from the Sun. More than one astronomical unit, but a perihelion of less than one. In other words, they can cross the orbit of the Earth. Odd objects have a semi-major axis interior to that of the Earth, but the majority of them have sufficiently elliptical orbits that they still cross that of the Earth. And then there are the amors, which are really more appropriately called Mars crossers. They don't quite cross the orbit of the Earth, but they have close approach distances that are within about 0.3 AU of the Earth. So they can get close to us, but they can't hit us. This over here breaks down the current percentage of each of these groups. About half of them are Apollos, just under 10% are the Oddans, and 42% currently are known as the Amors. So, cutting right to the chase, why do we care? Why do we want to study near-Earth asteroids? I mean, what's the big deal? From the public's perspective, And from a very pragmatic perspective of self-preservation, there's the impact hazard. These objects do occasionally hit the Earth. We want to avoid that. And I'll show you good examples of why we want to avoid that. Scientifically, they're extremely important. They are the sources of meteorites. Meteorites have told us most of what we know about the very early history of the solar system. Objects like these up here, and in particular, objects like this one. This is the Allende meteorite that fell in Mexico. It's a carbonaceous chondrite. It's a meteorite that has some very primitive carbonaceous materials in it, including amino acids. Much of what we know about the early formation of our solar system comes from meteorites. Meteorites come from near-Earth asteroids. The near-Earth asteroids themselves are the little bits and pieces that are still floating around after the solar system formed more than 4.5 billion years ago. Now, many of them have been processed. They aren't just things that have been existing as these little lumps that whole time. They mostly were parts of other larger objects that have been busted up, ejected off. Some of them have been compacted, some of them have been thermally processed, some of them have even had aqueous alteration in them. They've gone through a number of different processes. But they can tell us a lot about early solar system history. They also are very important because they do hit things, not only the Earth but the Moon. They are the dominant source of geology on the Moon by hitting the Moon. They also play a very important role in the surface of, say, Venus, Mars, the planet Mercury, on the surfaces of other asteroids, which we are exploring now, not only with telescopes but also with spacecraft. Some of them are inactive comets or maybe dead comets. How many, we don't know. Percentages, the most recent numbers are perhaps as many as 10%. I think most of us feel it's probably less than that, but it's hard to really tell. Some of them do have metal in them. Some of them are also known to have water in them. Now, when I say water, I don't mean liquid water on the surface, or necessarily not even just ice on the surface. It could be water in the form of phyllosilicates, minerals like serpentine, which has a lot of water locked up in its crystal structure. Asbestos, for example, is a type of mineral that has water in its crystal structure. Serpentine is, in other words, it's closely related to asbestos. Some of them even have minerals that are similar to clays. Clays have a lot of water in them as well. This is important in part because if we go there with, say, astronauts, these are sources of these are potential resources that we can utilize. Water in particular will be quite valuable. We need that, of course, to stay alive. A number of these objects are being considered as targets for robotic spacecraft missions. Two have already been visited by robotic spacecraft. One by NASA's Near-Earth Asteroid Rendezvous mission about 10 years ago. The second was the Hayabusa mission from Japan that visited an asteroid called Itokawa 5 years ago. And there was also an attempt by the former Star Wars organization to visit an asteroid in 1994, a flyby that ultimately failed because of malfunction by the spacecraft. It never got that far. And there are others that are likely. Japan is building another one, and I'll say a little bit more about that later on. Furthermore, and very recently, in April, President Obama made a speech that regrettably was largely ignored by most of the media in this country, where he signaled a fundamental shift in the human spaceflight program within NASA. He abandoned plans to go back to the Moon in favor of the ultimate objective of going to Mars, but going to Earth-approaching asteroids as a stepping stone. A target that is far more difficult to reach than the Moon is, much more distant than the Moon, and a very radically different type of environment, much lower gravity, just extremely, very, very different. Objects that could easily be more than a tenth of an astronomical unit away from us. Truly deep space missions that could last months. A very different kind of program. As a result of this, there is considerable interest in finding more near-Earth asteroids because of the ones we currently know about, there are very few that are reachable by spacecraft in less than a few months. Very few, unless we develop a new type of propulsion system. So let's give you a little bit of history. In 1900, there was only one known Earth-approaching asteroid. It's right there. That was 433 Eros. It was discovered in 1898. The other objects here, these other dots, are main belt asteroids, and also shown for scale are the positions of the inner four planets, and of course the sun here in the middle. If we fast forward a few decades, up to 1950, again, hundreds of main belt asteroids, and unfortunately the way that this is projected is a little bit hard to see, but there are a number of red dots that indicate Earth-approaching objects too. Here, there. There are, at this point, around 1950, I think there were about 15 or so, 10 or 15. Then we jump forward. Let's see, the first real search efforts began in the 1970s. By the late 1990s, we were really searching for them, primarily with the Lincoln Laboratories linear program the Space Watch program at the University of Arizona, JPL's Near-Earth Asteroid Tracking program, and their predecessor photographic programs that had been done in Palomar with the 18-inch Schmidt by Gina Carolyn Shoemaker and Eleanor Helene. At this point in 1999, there were hundreds of near-Earth asteroids now. And then if we fast forward to today, this is what we were facing as of 0 hours Universal Time on September 27th, which was a little over 24 hours ago. Green ones are main-belt asteroids. The red ones are the Earth crossers. The yellow ones, I think, are the ones that get close to Earth but don't cross it. There are some projection effects here too, because this is projecting a 3D solar system onto your 2D plane of the figure. So some things may seem to be crossing the Earth's orbit, but in fact they're above or below it. You can see that there are enormous numbers of objects now. The Earth crossing area is just, well, we're really living in a shooting gallery, a zoo of objects that closely approach us. Now, if we zoom in a little more closely to the vicinity of the Earth,
how big are they in general?
We'll get to that. Okay. We'll get to that. So this is the trajectory of the Earth. Earth is here. This red oval that's perhaps somewhat visible is 10 lunar distances away from the Earth. Everything shown here is within 0.3 astronomical units of the Earth. The arrows are an attempt to show whether it's above or below the plane of the solar system, which effectively is the plane of the Earth's orbit. And all these little busy labels here are the individual objects. The closest one is a very small object, about 30 meters in diameter, called 2009 SH2, that we are planning to observe at Arecibo beginning shortly after midnight tonight. We hope, if things work well. So the Earth, near-Earth region is a very, didn't want that, very busy place. So how many are there? Well, here's the answer to your question. Currently, just over 7,200 are known. Of those, about 1,100 are classified as potentially hazardous. Now, what do we mean by that? Well, potentially hazardous simply indicates that an object can approach within a certain distance, which is 5/100ths of an astronomical unit, and that it's big enough that if it hit the atmosphere, it would cause devastating effects underneath. Most of it, or at least a significant amount of it, would deposit its energy on the ground. The size threshold is about 140 meters. In practice, though, smaller objects could do a lot of damage, like the Tunguska event 100 years ago, which we'll talk about, was quite a bit smaller than that. But the Minor Planet Center, which is at the Harvard-Smithsonian Center for Astrophysics, adopted that definition, and so that's what we're dealing with in terms of potentially hazardous. It's a bit of a misnomer, because smaller objects can be quite dangerous, and they hit more frequently. In fact, this table here shows that. So we think that there are about 940, we estimate about 940 bigger than a kilometer, impact on average about once every million years. And then so forth down to 10 meters, could be 50 million of them, and that's what a ballpark, and those hit pretty frequently. One of those hit us last fall. And I'll tell you about that. Just under a year ago, I'll tell you about that in a moment. As of today, we know of 3 that are bigger than 10 kilometers, and our census of objects that big is complete. There aren't any left to be discovered. Among objects more than a kilometer, we still have over 100 that we think are out there, well over 100. We found about 85% of the ones that we think exist. Among objects 100 meters in diameter, we found a very small percentage. We think there are a couple 100,000, and we found about 5,000. And of course, you get down to the 10-meter size, and we barely found any. Now, as a result of this, our knowledge about their physical properties is really quite meager. We have studied a number of them with, say, spectroscopy to understand what they're made of. We've observed 263 with radar now, which can tell us a lot about their sizes and shapes and physical properties. But that's a very small drop in the bucket for how many are known to exist. Even among the ones we found already, we just haven't been able to keep up with the rate of discovery. So, as I mentioned, they do hit the Earth. This figure shows the geographic distribution of impact craters on the Earth. There are just over 160 of them shown here. The figure is a little bit old now. It's about 10 years old, and there are a number that have been discovered that it doesn't show. The most recent one was one that was found here in southern Egypt, found by somebody using Google Earth, of all things. The fellow in Italy who was just looking around in satellite images in Google Earth trying to find round structures. They found one in the desert in eastern Egypt. They mounted an expedition, and lo and behold, it's a crater about 4,000 years old. It's around, I think, 20 or 30 meters across. It's the most recent one that's been discovered. There's one off the coast of southern Chile that isn't shown here. There's another one that I'll show you a picture of in Peru, near the border between Peru and Bolivia that's not shown, and then some other smaller ones as well. But there are about 160 here shown. The largest ones, for example, this one here, the Chicxulub event in the Yucatan, that's the one that ended the era of the dinosaurs about 65 million years ago. There's some other very large ones. There's a very large one here in Quebec, Manicouagan, in the order of 100 kilometers in diameter. And some other also very large ones. Chicoutimi on the St. Lawrence area, that's another very large one, tens of kilometers in diameter. There's a very large one up here in Siberia. In fact, that's, I think, a double. There's a huge one down here, Bredevoort structure in South Africa, which is close to 200 kilometers in diameter, but extremely old, highly eroded. So these things do hit the Earth. This is one of the more recent ones. I hope you have been there. Certainly hope you recognize it. This is Meteor Crater, which is near Flagstaff, Arizona. It's a tourist attraction. You can go visit it. It's a short distance south of Interstate 40, a little bit east of Flagstaff. It's privately owned by the Behringer family. They bought it more than 100 years ago, hoping that they could mine all the metal they thought would be at the bottom. It turns out there isn't any metal at the bottom. They didn't understand that when an object hits, the material largely gets vaporized in the impact process. So there was really no major metal deposit to mine. But it's turned out to be a very useful tourist attraction, so they still own it. And they're very active in the astronomical and meteoritical community. They sponsor fellowships and help graduate students attend major international conferences and so forth. And members of the family regularly attend the Meteoritical Society meetings. I have a piece of the Behringer, of the meteor that formed that crater right here in my hand. It's made of metal. It's all rusty because it was sitting on the ground for about 50,000 years. In fact, you can buy these at rock shops, which is pretty much where I picked this up. So you're welcome to come on up afterward and have a look at that. So Meteor Crater is a little over a kilometer in diameter. It's about 50,000 years old. And we estimate that the object that formed it was about 30 or 50 meters in diameter. More recently, just over 100 years ago, 102 years ago, there was the Tunguska event in Siberia. There were no pictures of the event immediately after this happened. But 20 years later, about 10 years later, there was an expedition that the Soviet Union mounted to explore the area, and they found this vast region with the trees knocked flat. Except if you plotted out their distribution, they were knocked flat radially away from this one place in the center where the trees were still standing, but the branches were stripped away. This was an airburst event. There was no detonation on the surface. An object entered the Earth's atmosphere and exploded, we think about 20 kilometers above the surface, caused an enormous explosion. And this figure here shows the outline to scale with the greater Los Angeles area, showing the region that was devastated where the trees were knocked flat. The size of this object has been the subject of a lot of debate, the object that came in and caused this detonation. The current thinking suggests that it might have been as small as around 30 meters. Earlier estimates suggested around 70 meters. Very likely a rocky object, probably made of material called an ordinary chondrite. In fact, I have an ordinary chondrite meteorite up here. I have, here's one of them, I have a couple of them. It's the most common type of meteorite. They tend to be relatively fragile. Events like this are thought to happen once every few centuries. So think about that. Once every few centuries, let's say a typical human lives to be maybe 75 or 80 years old, there's a several % chance that something like this could happen during your lifetime. That chance is not zero. And that's a pretty high probability. And of course, the Earth is a big place, and 70% of the surface of the Earth is covered with oceans. So the chance that it will happen where you happen to be is very small. But the chance that it will happen where somebody might be is not quite so small. And eventually this is going to happen again if we don't do anything. That's one of the things we're trying to prevent.
When you say blast, what did that actually mean? Did it just disintegrate, or did it explode? Was there a secondary reaction?
It exploded. It exploded. There was one eyewitness that we know of, a fellow who was sitting on his porch, and an airburst went whipping by and knocked him off of his chair. The temperature went up, and he was quite a distance away from the center of it. It would have looked something like this, but even much brighter and probably higher.
So it ablated and it exploded, in a sense, it vaporized?
It exploded, yeah. What happens is, as the object comes plunging through the atmosphere, it builds up a tremendous amount of pressure in front of the incoming object, but behind it there's almost the vacuum. There's a huge pressure gradient across it, and when that exceeds the strength of the material, it just disintegrates very rapidly, in a very rapid cascade. Now if you have something big enough and strong enough, for example, made of metal like this one, this was an event in Russia in 1947, Metals are a lot stronger, and so you tend to have smaller ones that reach the surface intact than if they're made of rocky materials. One of the inferences is that the rocky materials are simply not as strong. They're not as compact. In fact, many of them we think are collections of blocks. They aren't cohesive objects, whereas the metal ones usually are. As far as we know, which isn't really, with metal ones, there's a lot we don't know. Another more recent event in 1972, a daytime fireball seen over the Grand Tetons. There it is. There's the trace of it. This is an object that penetrated into the Earth's atmosphere and then went back out into space. It was the first time we saw that happen. It's now been seen a number of times. It's thought to be about 10 meters in diameter. This one may be familiar to you. In 1992, there was a very prominent meteorite fall in Peekskill, New York. It happened on a Friday night. Thousands of people saw it because they were outside watching high school football games in like Ohio, Pennsylvania, New York, Maryland, states in the Northeast. This is a photograph of the event from a newspaper photographer, I think in Pennsylvania. It hit somebody's car. A high school student who very promptly sold the car and the meteorite for $50,000. I was a graduate student when this happened. I wish that had happened to my car. That would so this is the Peekskill meteorite. There's the meteorite right there, one of the pieces of it. In fact, you can see this. It occasionally travels around the world on display. This figure here shows you the trajectory of a number of meteorites, where they were before they hit the Earth. The Peekskill event is this one right here. This is the orbit of Jupiter for scale. So there have been between 5 and 10 meteorites now that have been observed sufficiently well through either photographic or video methods to figure out their orbits around the sun prior to the impact. In fact, we're making great progress with this nowadays because so many police cars have video cameras on their dashboards, and they're making them available whenever there's a bright event, particularly in Canada. Also, there are a lot of surveillance cameras in places like gas stations and banks. And so it's been possible to get the records when there's some event, some place to figure things out. Like, for example, there was a bright meteorite in Salt Lake City less than a year ago, where people were able to do things like that, take a look at video camera results from surveillance cameras to figure out the trajectories. More recently, a couple of years ago, 2008 TC3 burst on the scene. This was a small asteroid discovered by the Catalina Sky Survey near Tucson. It was the first asteroid found before it hit the Earth. A very small object, smaller than this room. We think about 10 feet across. It was discovered less than 24 hours before it hit. Here's the trajectory as it came in toward Earth. Here's the Earth. Everything here is to scale. This object was observed by hundreds of amateur astronomers, primarily in Europe. In fact, some astronomers in Spain followed it until it went into the Earth's shadow, less than an hour before it hit the atmosphere. And then when it did hit the atmosphere, it left this trail. This is a cell phone picture from somebody in Sudan. It actually hit the atmosphere over Sudan. It exploded, but fragments of it, such as this one, and that one, reached the surface. And this is Peter Jeniskens, the scientist from the NASA Ames Research Center, who led the expedition there in December of 2008 to search for fragments. He had the motivation to go and do it, and it was successful. They got a bunch of students, university students from the University of Khartoum physics department. They spread out over about 2 kilometers. They were, I think, 100 or 200 meters apart, and they, day after day, just marched forward like one big push broom, looking at all the rocks, trying to find something. And it didn't take that long. I think it was the end of the first day when one of the students found this little thing, like maybe a third the size of a fist. And then they ended up finding a couple hundred of them when all was said and done. And they've been back now for, I think, at least 2 expeditions and have found more of them. So this is the first time we saw one, and it came in and hit, and we were able to track it and able to measure what it was made of. And it turned out to be a very unusual compositional group that we've never seen before. More recent impacts, there was an impact in 2003 that punched through somebody's roof in Chicago. There's a meteorite right there. There's a hole in the ceiling. In September of 2007, an object hit near the shore of Lake Titicaca in Peru. This one was a real surprise because the crater was quite small, and from what we thought we knew theoretically, it shouldn't have reached the ground intact, but it did, and we still don't understand it. In 2009, there was a bright fireball over Indonesia. That's the one that I alluded to a few minutes ago. It was the most energetic atmospheric impact that we've witnessed since the Tunguska event.
May I ask,
Is there any international rules who owns the ownership of it?
Well, I think it's who owns something that
Yeah,
hits?
if you go there and you can just take it back.
No, you can't. You've got to work with the local government and probably the people who own the property if the property isn't owned by the government. There have been people who have been arrested for trying to smuggle meteorites out of countries in South America. A particular collector in Tucson named Robert Haig, who sells meteorites, and he's been arrested and kicked out of certain South American countries and is no longer allowed to go there because he's kind of broken the local laws. So if you find a meteorite in some other country, you got to be really careful. Even within the United States, I mean, if it's on someone's private property, it's theirs. Now, if you have some agreement where if you split it with them, if you find it, then that's a different story, and there are people who do that. But getting back to these other recent events, in 2009, in early October 2009, there was a very bright fireball seen over Indonesia, near the island of Sulawesi. And it was the most energetic event that we've seen so far. It was detected by U.S. Department of Defense surveillance satellites, who still haven't released their data. That's what they're designed to do, is to search for missiles, but they detect the thermal signature of meteorites as well. They detected it and were able to estimate the energy. And it was also seen by a lot of people. There was some more cell phone, video coverage and so forth. It also caused atmospheric pulses that traveled around the world that were picked up by microbarograph arrays that are in place to look for illicit nuclear bomb tests. And the consensus of the people who analyzed the data that is available is that the energy was several times that of the Hiroshima atomic bomb. About 3 to 4 times more energetic than the Hiroshima bomb.
Did it hit the ground?
No. It was an atmospheric detonation a number of kilometers above the surface.
So no damage on the ground?
No, there was no damage. It was in a very remote area and apparently over the ocean off the coast of Sulawesi.
Did it cause a magnetic effect?
No, it wouldn't. You wouldn't expect any magnetic effects. So, having said all this, what could we do? Well, the key thing to do is to find them before they find us. Find them early. We don't want to find them when they're on their final plunge, when they're just days or weeks before they're going to hit us. The search efforts are geared toward finding them years in advance. So you may see the media make a big deal of some asteroid and the astronomers didn't find it until it had already gone by us. Big deal. We found it. That's what counts. All these objects will go by there many, many times before they hit us. It doesn't matter whether we find it inbound or outbound as long as we find it before it hits. And that's basically what the search efforts, the statement here said. That we're trying to find them with a lot of advance notice. Once we do find them, then we need to know what they're made of, how big they are, what their mass is. Are they competent objects? Are they collections of blocks? How fast do they spin? Are they spinning in a regular manner, or are they doing something more complicated? Are they single objects, or are they doubles? Because it turns out that about 1 out of 6 of them are double objects. Even some of them are triple objects. For a small subset, we want to study them with spacecraft. But if we do need to deflect one, how would we do it? Well, people have put forth a number of ways we could deflect them. Some of them are quite fanciful. Others are exorbitantly expensive. The ones that the experts in the field have agreed on are the most technologically feasible are these 3. One would be to simply hit an object with one or perhaps a series of spacecraft years in advance, ideally decades. So if you just keep giving it small nudges, by the time it comes around to where the Earth is, it misses by a wide margin. You just want to keep hitting it. Another possibility is a so-called gravity tractor. That's a more subtle technique. The idea there is you build a massive spacecraft, you rendezvous with the asteroid, you stay close to it but a small distance away from it, and you thrust your spacecraft and just keep on thrusting it for years. And you very gradually use the mass of the spacecraft to tug on the asteroid and pull it aside. Even if you pull it aside a very small amount, even if it's only centimeters a year, if you do that for decades, it's enough that it will miss the Earth. If you don't have much time, then you have the nuclear option. That's the last resort. It gives you a lot of bang for the buck. There's no question about it. But it's also obviously the technique that is the most controversial internationally, because you'd have to, one, either change international law, or 2, ignore it, because there are treaties against nuclear explosions in space. But there's a lot we have to know about what this would do before we would do it. But there's no question that that would deliver the most energy in the shortest amount of time. And it would probably work. Making the world agree that we should do it would be a harder thing. The key is to find them, and find them as soon as you can. Now, the first question that people usually ask me is, are there any that we know of that have a chance of hitting us? In terms of any that have a chance of hitting us that are large enough to care about, not really. There was one that was discovered a few weeks ago that has a 5% chance of hitting us in about 80 years, but it's not much larger than this room. It'll just hit the atmosphere and disintegrate. No big deal. We don't really care. There are some other ones that have much, much smaller chances of hitting us sooner than that, but you're much more likely to, die by being hit by lightning than you are from those things hitting us. Certainly much more likely to be run over walking across the street. We haven't found any yet that we clearly can say have our name on. Not even close. So this figure lists the principal survey programs. These three are all at the University of Arizona, run by pretty much the same group. They're the leading search programs in the world right now. Linear has found a lot of them. They got up and running in 1997, and they have largely been superseded by these three, although I understand that they're developing a new system that's supposed to come online in roughly a year. Spacewatch has been running since the 1990s. They've discovered a lot of objects. WISE, that's a NASA JPL spacecraft, Wide Field Infrared Survey Explorer. They've discovered a little over 100 asteroids this year. Pan-STARRS is the next one that's just coming online. They found their first asteroid about a week and a half ago. And they, once they get fully operational, will probably swamp everybody. They're located on Maui, on Haleakala. Once we've found them, that's when radar starts to come in. So how do we study these objects? How do we investigate the physical properties? Radar is a very powerful technique. Light curves, that's measuring how the brightness varies as it spins with an optical telescope. Spectroscopy, using how they reflect and absorb infrared and visible sunlight. You can also look at their thermal infrared signature, the heat that they emit. That's a very useful way to figure out their sizes. In fact, that's what the Spitzer Space Telescope and the WISE telescope did. And they've studied hundreds of near-Earth asteroids. And they're really going to revolutionize the field. The results are just starting to come out. They're giving us much more information on the distribution of sizes. And of course, they're really starting then you go there with the spacecraft. You can't use optical telescopes, for example, the Hubble Space Telescope, to image near-Earth asteroids. They're simply too small and too far away. It won't work. Biggest ground-based telescope at optical wavelengths, the Keck telescopes, the very large telescope, even these other ones that are being built, they aren't big enough to really help you. They can't resolve them. At least not at levels that are useful. A little bit about the compositions. There are several compositional groups. I have examples of some of these up here in the table. Carbon-rich, some stony ones. Some of them are made of basalt, type of lava. Some of them are made of metal, and some very bright stony ones. Overall, there are more than 25 compositional groups that are recognized. They span a wide suite of rotational states. This shows spin rate here, logarithmic scale, or you can think of it also as rotation period. Fast here, slow there. Sizes, small here, big there. The near-Earth objects are shown with the big solid dots. They concentrate down here. By and large, they rotate more rapidly than the main belt asteroids. And their smallest ones are the most rapid rotators. There's a barrier of sorts here, which we think is caused by their strength. When you get to a certain size threshold, they're no longer collections of blocks. They're monolithic objects that are competent. They're strong. And they have enough cohesive strength that they can spin more rapidly than the ones that are collections of blocks. They're just held together very weakly by their rather diminutive gravity. There have been a number of spacecraft missions. I don't want to spend too much time on this, but I'll show you a couple of images. There are some coming. These are the first two. Japan is building one to go to this asteroid, the Hayabusa 2 mission. Some others that have been proposed for NASA but not yet funded. That's going to change, we think, in a very big way if President Obama's plan comes to fruition. NASA is seriously looking into and planning to start sending a flotilla of robotic spacecraft to near-Earth asteroids to prepare for sending humans in the middle of the next decade. Precursor missions. There are also a number of asteroids that have been visited by main belt spacecraft. Most recently, main belt asteroid Letitia visited by the European Space Agency Rosetta spacecraft in July. Here are some images of Eros. This was the NASA mission about 10 years ago. This is the second largest near-Earth asteroid, very elongated, about 30 kilometers on its long axis. It poses no threat to hitting us. Itokawa, this is the one visited by the Japanese Hayabusa mission 5 years ago. This is a more representative object of the near-Earth population. It's about 500 meters long, irregular in shape, elongated. It's a very interesting structure on its surface, a whole bunch of very large blocks. The consensus among the people in the field is that this is a prime example of a rubble pile object. one that is a collection of blocks. That's the way to think of it. And it's held together by its very weak gravity, with some sticking forces, but almost entirely by gravity. Okay, let's move on to radar. So, why do we want to study things with radar? Well, again, I'm getting a little bit ahead of myself. I'll tell you that in a moment. But before we do that, there are two telescopes that we use for radar observations. Here they are. Arecibo here on the left, Goldstone on the right. Arecibo is in Puerto Rico. It's about a 90-minute drive west of the city of San Juan. It's the largest single-dish telescope in the world. It has a diameter of 305 meters, which is 1,000 feet. It has a surface area of 18 acres. It's truly enormous. The dish itself is built into a valley, and because of its enormous size, the dish does not move. In order to steer the telescope, you can rotate this structure here. It can go around 2 full revolutions in azimuth, and the radar component is in this Dorian dome here, and that can move up and down on an altitude rail. So you can see basically the sky within 20 degrees of straight overhead at its latitude of 18 degrees north of the equator. You might think, well, gosh, that's very restrictive. Actually, it's not. You can still see 1/3 of the sky with this system, despite its rather limited pointing capabilities. By virtue of its size, Arecibo is extraordinarily sensitive. When things are working properly, it radiates 900,000 watts, between 900,000 and 950,000 watts. It's extremely sensitive. We regularly image Earth-approaching asteroids a 1/10 of the sun's distance away from us. Yes?
At what frequency?
Arecibo is primarily working at S-band, 2.38 gigahertz, 13 centimeters. Goldstone is shown here on the right. It's a 70-meter dish. It's part of the Deep Space Network that NASA operates. This is about a 3-hour drive from here. It's about 50 miles north of Barstow. It's fully steerable. It can see about 80% of the sky from its latitude of about 35 degrees north. It operates at X-band, 8.56 gigahertz, 3.5 centimeter wavelength. It has overall about 1/20th the sensitivity of Arecibo, but it can track objects for much longer because it's fully steerable, even farther south. It also, in addition to being able to track things longer, by virtue of its different frequency, it effectively has better frequency resolution, which is related to how things spin, which is very helpful. More recently, we've developed a new imaging capability there, which I'll show you an example of. We can see things at higher spatial resolution now with Goldstone as well. Goldstone is not as sensitive. It's only 1/20th as sensitive as Arecibo, but it can follow objects for longer as they go across the sky and observe them at higher resolution. So the two telescopes have very complementary capabilities, and that's something that we exploit on a regular basis. Another misperception about Arecibo is that by virtue of its somewhat limited pointing is that we can't track very many objects. That's actually not true, because most objects pass within its range of declination eventually. And it's so sensitive that we can often see things at considerable distances, typically twice what we can at Goldstone. And so at some point they usually do traverse its range. For example, we observed an object about 300 meters across at 1/4 the distance between the Earth and the Sun. Now, I'm up here representing a fairly large number of people now. It's not just me. The real founder of this field is Steve Ostro, my former supervisor at JPL. Steve and I worked very closely until his death from cancer about 2 years ago. He was really the godfather, both figuratively and literally, for our field. It really helped establish a lot of what I'm going to show you. And he also helped to train many of the people you see on this list. So why use radar? The primary reason is given at the top. Because it's an extremely powerful telescopic technique for studying near-Earth asteroids, their physical properties,